So that's why everyone's here to say hi.
So you have to introduce just.
Yeah.
All right.
Okay, it's a great pleasure to have Rick here today. I looked around, so you are originally from Brazil. You finished your bachelor in the University of Campinas.
Yep.
And then Sao Paulo University was for a master.
Mm-hmm.
And then since September 2020, you are at University of Waterloo. And also, I think you're associated to PERCHE Institute. And you're lucky guys there. You can associate all the good institutions over there. And okay, so today, I'm curious to hear how something classical can entangle these things. So
We're going to discuss it.
Very controversial talk, so I'm looking forward to it.
All right, thanks, Jaslav. Yeah, it's a pleasure for me to be here as well. I've never delivered an international talk in person, so in a way, like this is a first time for me. So yeah, thanks a lot for the invite and for the accommodation, for everything. And Eduardo, of course. So I don't know what's going on. But okay, so Eduardo apologizes that he can't be here right now. He actually started feeling sick since Friday, and he tested positive for COVID yesterday, so that's why he's not here. And yeah, the projector, yeah, I don't know what to do here, sorry. Yeah, I'm trying to tweak it. Well, I can. I don't know, we connected both. I don't know which one is actually providing the. All right, there you go. It's back. Hopefully it's. Okay, cool. Okay, I'm just gonna come back. All right. Sorry about that. Okay, so Eduardo apologizes that he's not here today because he tested positive for COVID, and but essentially I'm going to be presenting two works that we've done together. One of them is published in the archive. That's the archive link, and it's about essentially the BMV experiment and well, what are the conclusions that can be drawn from the experiment? And the other one is work in progress that should be out this week. A condition that Eduardo starts feeling better and that we can actually finish reviewing the draft. Else it's going to be next week or a little bit later. But yeah, so okay, so the idea of the talk essentially will be to talk about comparing classical and quantum fields and relativistic quantum information protocols. And as Jaslav said, this is a controversial topic. I don't think it's a controversial topic. I think it's a controversial name, perhaps, to call it classical fields. But we should definitely debate about that. So, well, okay. So the outline of the talk is I'm going to give a brief introduction. Then we're going to talk about this whole comparison of classical and quantum fields, essentially. So we're just going to review how to source classical fields, things source classical fields. Then we're going to specifically talk about how quantum systems can source classical fields, in a sense. Then we'll talk about how quantum systems interact with quantum fields. And then from this point on, we can start comparing communication and entangling protocols in relativistic settings using these two different models. And then, after summarizing what we learned from this comparison, we're going to finally apply this to quantum gravity and the BMV experiment, right? Which I think that is the topic that, well, personally I find the most interesting, but I think that this whole comparison is interesting by itself. Okay, so all interactions in the standard model are described in terms of quantum fields, right? So if I give you two spins, or if I give you most systems that you could think of describing in terms of the electromagnetism, the weak force, strong force even, you're going to think of using quantum fields. Well, not really, right? If I give you two quantum systems, usually what you think of doing is simply writing an interaction between these two systems, and then, well, you don't think about QED, for instance, to write the interaction of a spin-spin system. What you do is, well, there are two spins, and the Hamiltonian that controls the interaction between them is this J coupling, which is sigma A, sigma B. That's what most of us would do without thinking about QED, right? So the question is, what's going on here? Where's the QED if according to the standard model, fundamentally all interactions should be mediated by quantum fields? Well, the first thing to be noticed here is that it's not really that this interaction is something like that. What happens is that, well, spin B sources a magnetic field which interacts with spin A, and then A feels this magnetic field because coupled to the magnetic field itself. And the same thing happens with spin A. It also sources a magnetic field that interacts with spin B. And then we get two terms like this, essentially, where this is the magnetic field that is sourced by system B, which just so happens to be proportional to the Pauli matrix of system B. And the same thing is true for system A. So in the end, this is a way of writing an interaction of system with field and system with field, such that the fields are proportional to the observables that source the field, that couple to the field. That's essentially what's going on here. And of course, you could go to QED and you could describe these things in terms of QED and then do suitable approximations and reach this conclusion. Of course, you could. Another example is, for instance, the hydrogen atom. I think that, well, when people first came up with the idea of the hydrogen atom, they had classical electromagnetism, the Coulomb potential. Then they said, well, what if this thing is applied to quantum systems, to a proton and an electron? Then they did write down this potential, and then they solved the Schrodinger equation. They found the bound states. They solved the hydrogen atom, right? Again, there's no QED here, but nowadays, if we want to recover this from QED, we could write down the full QED, employ a lot of approximations. There are a lot of assumptions, and we could actually reach something that looks like that would work under in some regimes. So the issue here, or it's not an issue, it's a property of these approximations that we would have to employ, is that these end up requiring non-relativistic assumptions. So they're not going to be suitable if you want to talk about causality, space-time, relativity, or gravity in general. So if we want to employ some sort of approximate or a different model that is not quantum field theory in order to talk about gravity, we can't be violating any of these. We can't just use any model which is, say, a Newtonian potential, which looks like this. Okay? We would need to do something which at least would not violate relativity. So our goal for the talk, essentially the first goals will be essentially to first describe these relativistic quantum information protocols using classical and quantum fields. That's the first thing we want to do. Then we want to compare the two and to understand the difference between using fully featured quantum fields to model the interaction or to just use classical fields in these processes. And then we want to determine the regimes where the classical and the quantum fields give different or similar results. And then we want to look for experiments which will explore the cases where the quantum fields cannot be well approximated by the classical model, because that is the thing that would actually give us evidence about where gravity would be, where we could test whether the field is quantum or not. And then finally, of course, we want to apply this to the BMV experiment and the whole quantum gravity idea. Okay? So I'm using the word classical a lot. We're going to get to a point where we're going to be able to decide whether to call this field classical or not. I'm going to keep using the name classical, but I'm going to specify what I mean by this after we describe everything. So first things first, let's talk about classical systems that source classical fields, how classical fields are sourced. Okay? So classical fields can essentially be seen as as a consequence of the matter that sources them, in the sense that if I give you some current that couples to a field, then you simply integrate that with respect to the retarded Green's function. This is going to give you the classical field at any point of space. If I start with a charge here and I move it around a little bit, it's going to produce electromagnetic fluctuations that will all be contained in the retarded propagation of the motion of this charge. Everything here is classical. Everything here is classical. The source is classical. The field is classical. Everything is classical. Okay? We're going to start adding quantum ingredients later, and I'll try to be very clear when it does. When you start seeing the color red, it's usually an indicator of quantum. Classical fields are always blue. All right, so except for this. This is just to indicate that this A here is just any collection of Lorentz indices. So this could be a scalar field. We want to apply this to gravity later, so that's why I'm using this kind of general formalism. But in essence, it could also be used to electromagnetism. For spin systems, it's more complicated to come up with classical ones, but in any case, the idea is that, yeah, this A, don't be scared of it. It's just could be a mu, could be a mu nu, could be nothing. It would just be a scalar field. Now, OK, cool. So, and then in this context, if we want to write the field as being sourced by this matter and just being the consequence of the retarded Green's function, then the field is going to be entirely determined by the matter that sourced this field in the past, right? If I know all of where matter is at all points in space-time, then I can just propagate this and find out what's the state of the field. So in a way, the field's degrees of freedom are kind of completely determined by the matter that sources it. Okay? So the field's degrees of freedom kind of become completely determined by the matter, okay? And encoded in the retarded Green's function. So we want to later apply this to communication protocols, so we're going to need to talk about more than one system. So what happens if you have two systems which couple to a field phi? Now, the dynamics of these systems could be implemented by, well, free Hamiltonian for, do we have a pointer? Yes, free Hamiltonian detector A, free Hamiltonian detector B. And then there's this term here, which I want to try to explain to you what it means, okay? So the idea is, if you have a system A and it's undergoing a trajectory, right? So say that system A is undergoing this trajectory, it's going to source a field, right? There'll be a field which will be associated with the state of the current that sources this field. And then what's going to happen is it's going to source this field. I'm calling it phi subindex A, okay? This is the field sourced by the particle A undergoing this trajectory. Then if you place a particle B here, the particle B will feel the effect of this field at this point where its current is situated, okay? And the same thing is going to be true on the other side, which is particle B will also source a field, and it will be felt by the current that couples to field A at this point. So this is the interaction between the two systems. There's nothing fancy. We're going to say that this is going to recover exactly what we expect, for instance, for the case of the spin-spin systems and any other, well, the hydrogen atom even, because we're going to be able to write everything in terms of the Green's function later.
Just in your explanation here, there is just something weird that x and you have two different points.
I'm sorry?
In your integration, you have just one x. In your picture, the points of interactions are distinct.
So essentially, you can think of this as like me integrating over the spaceless. So if I were integrating over this spaceless, what would happen is the support of this current would be just on top of the curve B, because the current of B. The support of this one would be just on top of the curve A. So I'm actually only integrating, I'm just going to be adding the value of this current with the field at this point, at this point, and the current with the field at this point. Then you have these two, and that's what you're actually doing here. You're just integrating this because, again, this will kind of become more natural when we add the Green's functions. But does it make sense? Okay. And of course, we're going to have a coupling constant. You can think this is a charge, well, whatever, doesn't really matter. It's just a coupling constant so that we can control things for a general field. In the case of gravity, it's going to be G. In the case of electromagnetism, would be electric charge. Well, that's it. And this is what we're going to call the interaction Hamiltonian. And if we work a little bit with it, so essentially the idea is that we can replace these fields, phi A and phi B, by it's what is sourced by particle A and particle B, right? So this index here is just labeling the A or B. So I'm just replacing the field by the retarded Green's function. And now if I place this, if I look at this retarded propagation, so for instance, in the case of a massless scalar field and inertial trajectories, this would just be this would simply be the retarded time. This will be evaluating the retarded time and dividing by the distance between them, okay? So this is a 1/r potential, essentially, for a Klein-Gordon field set. And this is what would show up here, and you just have the product of the charges, but at different times, and the 1/r distance between. And if you just place this retarded Green's function there, what you find is that you can simplify a little bit the expression. So you just find that your Hamiltonian is this propagated version of the currents sourced by A and B, now coupled with the other ones. And this is the Hamiltonian that would essentially describe the general model. We're going to simplify this a lot because I don't want to be working with this thing here. I'm just going to note that if you integrate this Hamiltonian over T, you get this result here, okay? And this result is a little bit simpler, where delta here is what's called the radiation Green's function, or I'm just going to call it delta, but it's essentially the retarded plus advanced propagator. And if you're wondering how the advanced propagator shows up there, the advanced propagator is just the retarded with the points switched. So if you just perform a change of variables there after you integrate over time, then you can just obtain something like this. And this is going to be very important for us because when we get to quantum field theory, this is going to show up in the Feynman propagator. And it's going to be essential for us to recover the classical results from the quantum ones, okay? Nice. So I think that the lesson here is that the role of the field in that Hamiltonian there is entirely played by the retarded propagation in the model, right? So there's no field anymore. If I just want to talk about particles A and B, I don't need to talk about the field because all of the 1/r potential and everything is already encoded in this Green's function, okay? Nice. Cool. So let's just simplify then the model because we don't want to be working with a general thing. I'm just going to go to a classical case. So just assume that we have scalar monopoles and fixed trajectories and a Klein-Gordon field. So the field is just massless Klein-Gordon, okay? It's going to be easier for us to understand, to picture what's going on. And also, the expression becomes simplified, because then the current is simply going to be given by the monopole and a delta that localizes it in the curves. And the interaction Hamiltonian will then be, well, just the monopoles, but now with the retarded propagation from the curve A to the curve B. And so from the curve, this is what's sourced by B, this is what's sourced by A. You just add them together. And again, reminder that this is essentially 1/3 the distance between them and the retarded time. If you're in a limit where the retarded time is actually the time, what you're doing here is that you're simply getting the product of the two monopoles divided by the distance between them. This is kind of similar to what we had in the case of the spin-spin coupling, but they weren't scalar monopoles. They were full sigma matrices. It's harder to do this with electromagnetism because of the indices, but the idea is that this thing here ends up becoming, in many cases, just constant times the product of one and the other. They're not operators yet, but they're going to become so. OK, cool. So this is how it works with classical systems. Now, how does it work if we want to modify the setup to contain now quantum systems instead of classical systems? So remember that the Hamiltonian that we had there in the end, it doesn't have any field there. It doesn't have any classical field anymore because we already used all of the properties of the classical field when we wrote down the retarded Green's function. So now, if we want to consider quantum systems that source this field instead, well, there's a very simple way of doing this. And we literally put hats on the muse. Because if we had classical systems coupled to classical fields before, now if we have quantum systems with the same coupling, we can call this the coupling of quantum systems with a classical field. So this is what I'm going to mean by classical field model. Okay? So just put a hat on the muse. Nice. So explicitly, if we want to look at the same example that we were doing before, we could think that these monopoles live in this Hilbert space C2. They're operators in this Hilbert space C2. I'm going to consider the monopole just to be this sigma x, so that we have a clear model in mind. And then we have to talk about the free Hamiltonian, the free evolution of each one of the individual models, so that if you want to have a concrete picture in mind. So I'm just going to pick qubits with gap omega. Okay? And in this case, then we can just write down the Hamiltonian for the interaction. So you're going to see that it's essentially the muse with the hats. And I added extra terms here. These are not explicitly speaking necessary, but they're good if we want to talk about local interactions. So essentially, these are switching functions. So these are just functions that are going to control when the interactions are happening in time. Okay, so you can just picture this as something that will make the interactions not last forever, but just last for a finite amount of time. Maybe it's a Gaussian that goes up and down, or maybe it could be one if you wanted the interaction to be determined forever. So they're just going to be there because they're important later for localizing the interaction for communication and entangling protocols. Cool, but this is the interaction. And just final reminder, right? So if you plug back this, you're going to get something which is simply the product of the two field operators. Retarded time, if you're in a non-relativistic limit, it's just the product of mu A, mu B. And this starts starting to look like the interaction of just two spins, right? And indeed, it's supposed to be something like this in the non-relativistic limit, in the case where the detectors are inertial and co-moving and things like this. But in general, if you want to respect the causal structure of spacetime, you have to take into account the retarded propagation of the field. Okay? So that's essentially what's going on here. Nice. So if we want to do a concrete example now with this thing, we just need to say what is the initial state of the quantum systems. So say that they're both in their ground states. So I'm using GA and GB to denote these. Then if we apply the time evolution that comes with this model, well, you obtain this matrix here to leading order in perturbation theory and lambda. And these MC terms, what they end up being are essentially integrals of the delta propagator, which is the retarded plus advanced, right, that we mentioned earlier. Here we have the switching functions. So essentially this is propagating one switching function to the other and the other to the one, which is essentially propagating the field, taking into account the decay that comes with the retarded Green's function. And there's a Fourier transform term here that comes from the that comes from the energy gap of the systems. And also, of course, if you wanted, you could just write this as a vector, because these are two quantum systems interacting unitarily. They start in a pure state, they're going to end up in a pure state, right? So, okay, this is the classical model that I wanted to present and discuss, okay? So, now the question, is the field classical? Okay, I think that's the question that has to be addressed. So, I think the answer is very clear. It's, well, it depends. And, well, let's ask other questions that can help us understand what's going on. Does the field have any quantum degrees of freedom? Well, no, it doesn't have any quantum degrees of freedom. There's nothing that even resembles a quantum degree of freedom there. And in fact, we're going to see later that this model is obtained from a quantum field when one gets rid of all of the quantum properties of the field. We're going to do this soon, okay? So I wouldn't say that this model has quantum degrees of freedom. It's definitely not a fully featured quantum field. Now, can the field be in a superposition? That's another question you could ask, because what if the sources are in superposition? Then what of the field, right? Well, the field is entirely determined by the states of matter, which can be in superposition. So it could be fair to say that the field is in a superposition. But we have another issue here, which is that, you see, there's no Hilbert space for the field. So I don't know what you would mean by superposition in this case, but if you want to come up with a definition of superposition that doesn't involve Hilbert space, in the context of quantum physics, sure, we could maybe say that it is in a superposition. So yeah, this is what I have to say essentially about it. But I think that maybe something which is worth mentioning is that another name for this model is quantum-controlled classical, okay? Which makes it evident that the quantum part is the one that really is in the sources, not in the field, okay? So I don't know if you want to call this a classical field, but I think that the lesson is you should definitely not call this a quantum field. There's nothing quantum about that field whatsoever. The only quantum part is on the sources. Yeah.
I don't want to really go into the issue, so if you want to call it classical, you can go on.
No, yeah, I agree that classical is a bad name in the sense that I agree that you can't always define one field that is at every point of space and time, right? So I agree with that for sure.
No, I haven't finished, sorry.
Oh, sorry.
So, I mean, you say there is no Hilbert space for the field. Well, this seems like there is no degrees of freedom of the field because it's slave to matter. But then it's not a field at all. Like, it's not classical because either there is degree freedom or there is no degree freedom. If there is no degree freedom, I'm fine with this. So we talk only about matter. But if there is degree freedom, well, then the fact that you can violate, for example, in DMV setup, inequalities like probe particles, that of course you can understand as direct interaction with the mass, but via the field, I would hesitate to call it classical. But I do understand what you want to do next, so there should be a distinction between these two notions. I think it's just classical doesn't sound the best choice.
There's another question one can ask. I mean, if you have the field sourced by quantum matter, you can still ask, can I measure it with arbitrary precision? Or if you have several components, or like electric field and magnetic field, what are their Heisenberg type of commutation relations? And then in that sense it would be
Classical here, in that case.
Yeah.
The next step that he wants.
if under certain conditions. For instance, if everything is static.
So the question is whether there is some kind of like Heisenberg uncertainty relations for the field, right? But that's something, I think it's hard to answer something like this. Because even if you found something, it would literally just be a consequence of the Heisenberg uncertainty relations for the sources. So it's like, again, are you measuring something about the field? I wouldn't say so, but yeah, sorry.
You show again the equations that show how the quantum system is creating a classical field.
how it's sourcing a classical field. So you see, I never told you how it was, because in the end, the only thing that I said was they will interact according to this Hamiltonian, because this is the classical Hamiltonian, and it's, yeah.
Quantum systems are the two mules.
Yes, the quantum systems, each one of them has a,
Classical field which is source is what?
every role that it plays here is contained in the retarded Green's function, which tells you that if matter is at this position at this point of time, then a little bit later, the fact that this other matter is going to feel is going to be given by this.
So what is the classical field? Is that
The classical field doesn't show up here. What shows up here is the consequence that it has in interaction of the two particles, which is via the retarded Green's function, which is entirely classical.
okay, but so what is the classical field which is sourced by a quantum system? What is it?
I would say that it's entirely contained in the Green's function, the retarded Green's function. And the retarded Green's function has nothing quantum at all. It's just a classical.
The Green function itself is a classical field.
No, I'm saying that the classicality of the field is displayed in the fact that we're.
Sorry, it's very basic, but I don't understand the setup. I mean, what is the field of which you're talking about classicality? Which field in your system? What are the system? I see that you have two systems A and B, which are quantum systems, and that are described by mu. But then you are saying that these quantum systems, they are sourcing a classical field.
No, I'm saying that there is an interaction, which is the same interaction that would be seen if two classical systems were interacting via classical field. I'm saying that now there are two quantum systems that are interacting according to the same interaction. I'm not saying that there exists a classical field here. That's the thing that I said to Czeslaw before. It's like, it's not possible to define one field with one point, with one well-defined value at each point of space-time. You cannot do this, okay? So you cannot do that. What you can do is say that there's nothing quantum about the field in this interaction. Sorry, Catherine.
Margaret wants to say something to Czeslaw and Wolfgang, which is that the field could be a stochastic theory, but not necessarily quantum. Certainly, this is not a classical relativistic field, but stochastic theories can be classical. One needs to complement the description of the field with extra assumptions, and the model is agnostic about the underlying theory for the field. Hannes can say more about this too.
Yeah, what I'd like to do is like save the discussions that are more explicitly about the BMV experiment for later, so that we don't spend too much time now, because I'm still going to talk about the BMV, and I think that these are more, yeah.
I would like to respond, please.
Can we save the response to the end?
So,
Because I think that it would be nice to read this again in the end and then discuss it. I think that so that we don't spend too much time in the, okay? Because also, I must admit that I haven't had time to rehearse this thing. I finished it at 5 a.m. yesterday, so I don't know how long it's going to take. I think we're good. Okay, sorry. So let's save the questions that are more related to whether the field is classical or not, and whether this could tell us something about quantum gravity, which is where this is leading to the end. Okay, cool. So we do have a description for quantum systems coupled to classical fields. I'm going to keep calling it classical fields, but at least we all understand what I'm talking about in this case, right? It's this direct interaction that only uses classical properties of a field in order to provide interaction for two quantum systems. Now, although we only discussed this for monopoles coupled to scalar fields, all of this can be generalized to more general fields, to more general quantum systems, to more general fields as well. So we can use a model that's very similar to this one for gravity, and we're going to do it later. But for now, let's talk about quantum systems coupled to a quantum field, and let's see what would happen, whether we can recover this model, what are the differences between the two. Okay? So first, we need to briefly talk about QFT. So I have two slides that are going to give us everything we need about QFT for this. So quantum field theory can be formulated in terms of these smeared valued field operators, smeared operator-valued field operators. Well, that essentially act in test functions, right? So you can think of the field as this distribution, operator-valued distribution. And the key quantum property of the field is essentially implemented by this commutation relation here. So it essentially says that phi f and phi g, their commutator is I times this E. This E is also, it's a distribution, it's a double distribution. And it's essentially the retarded minus advanced propagators, okay? So important, this is a minus, okay? This is not the same delta that we had from before. when you're doing interactions with classical systems, you're never going to find a GR minus GA. You're never going to find a retarded minus advanced. You're always going to find retarded plus advanced, because the effect of one in the other plus the effect of the other in the one. So it's a product of the charges. You can't really get that. So this is the quantum property of the field that can be written in terms of the classical propagators. Okay? And this essentially implements the quantumness of the field. And once we're talking about quantum field theory, then we can talk about states. And then all of the predictions of a quantum field theory can be written in terms of a Whiteman function and the Feynman propagator. So the Whiteman function is just a two-point function. And it just so happens that its imaginary part is the E that we talked before, and it's also got a real part. And the Feynman propagator, which is a time-ordered two-point function, has its imaginary part as being I times the delta, plus some other term, which is the same real part as the Whiteman. This other real term is called the Hadamard function. So it's the expected value of the anticommutator of the field. And just a reminder that the delta and the E are given by the GR plus GA and GR minus J. Okay? So retarded plus advanced and retarded minus advanced. Now, important things here are, you see, these quantities here are only dependent on the equations of motion of the classical field. Okay? So, of course, these terms here cannot know anything about the quantum state at all. So all of the state dependence of the quantum field is contained in the Hadamard distribution. Okay? So essentially what happens is that these parts here are proportional to the identity. When you just write the field operator, the imaginary part that would come out here doesn't act trivially in the field in the state, and just the anticommutator part really matters. And this state-independent thing, which is just in terms of the GR and GA, is essentially a classical state-independent for the reason that we saw before. And I'm going to refer to this one as a quantum state-independent, because this is the one that defines the commutation relations between the quantum field, and the other one is the one that you get when you're doing radiation problems or mutual interaction between two classical systems, or quantum. Well, OK, so I just wanted to really highlight that there are state-independent and state-dependent parts, classical and quantum. Okay? Nice. So with this, now I can talk about how to couple quantum systems to quantum fields. The idea here is essentially, so we're going to keep doing the same simple model. So we're going to get a monopole moment that undergoes a trajectory z of t. So essentially, this is the Hamiltonian. So what's going to happen is we're going to have a switching function as well that's going to control where the interaction is going to happen. We're going to have the monopole moment, and we're going to have the field. And this is the interaction. If you're familiar with the UDW model, this is just a UDW model. This is the interaction of a qubit with a quantum field. But if you're not, it doesn't really matter. And for two quantum systems, what we're going to have will be two interactions that look like this with A and B. And you may notice at this point that the classical interaction was proportional to lambda squared. Okay, this one's proportional to lambda. So just to try to understand what's going on and how to see a little bit more of the classical interaction in this, you remember that what we will do in order to recover the classical interaction will be essentially to replace this field by the field sourced by B, and this field, this by the field sourced by B, yes, and this by the field sourced by A. And then this would become something like retarded Green's function of A, mu A, and the other one retarded Green's function of B, P.
Sorry, what's
Yeah.
lambda again? It's just a...
Lambda is the coupling constant. Yeah.
And why is it that in the classical model it was L squared?
Yes, that's what I'm explaining right now. Because what happens is you replace the field essentially by the retarded propagation of the current. And because the coupling with the current comes with the lambda, then if you plug this here, you get a lambda, you get a Green's function, and you get the current coupling, which is what we had before. So that's why. Okay. So in a way, the quantum model is like a square root of the classical model. Yeah.
So the lambda is contained in phi.
It's not it's contained in, because you see, if I give you an electron with charge E and I move it around, any field that you feel there is going to be proportional to E. And if you also have charge E, now the interaction between the two will be E times the field. My field will be proportional to E, so it's going to be E squared times the propagator. Make sense? So that's what's going on. That's why in the classical field we had the E squared, and the quantum field, well, you just say that you're feeling a field, and you have a charge E, and that's it. Yeah.
So you're saying as soon as the field is quantum, you no longer have lambda squared because you can't express it in terms of the Green's function?
You will get a lambda squared because this will naturally show up when we do perturbation theory, because then the Hamiltonian will start stacking. Yeah. But I'm just saying that it's like, in order to compare them, it's like it's just something that when you use this idea of replacing the field by the propagation of the current, then you're going to pick up another factor of lambda, right? Which is what happens there. Okay. I'll save it. Okay, so we can then consider the analogous setup to the one we did before, but now we can put, again, we're going to put both the qubits in the ground state, and we just run down the time evolution, right? So if you just run down the time evolution, the only thing is, here we have to pick a state for the quantum field, because now the quantum field has quantum degrees of freedom, it has its own Hilbert space. So if we pick the vacuum state, which is essentially picking the initial state for the whole system as being ground, and vacuum, now we can just run, apply the unitary time evolution. But importantly, we need to trace out the quantum field if we want to get just the state of the two systems. If we only have access to the two systems, we're going to have to trace out the quantum field. So if we do this, let me move this up there. So if we just do this, this is the final state that we get. And here, we have terms, so these L terms that show up there, they're essentially going to be integrals of the Weidmann function. Kind of the same structure that we had before with the omega and the e to the I omega and the two switching functions. And the M term here is going to be also kind of the same structure, different sign there, and the Feynman propagator instead of the Weidmann function. Okay. Now, if we want to compare this model with the classical one, now we can put them side by side. Okay. So in the quantum case, we found this. In the classical case, we found this. The L and the M terms were these two, and the classical M terms were was essentially this. Okay. So now, okay, let's recall what the W and the G are. Now, the imaginary part of the Green's function is I divided by 2 times the delta. So if we were to just replace GF by this, these two would match, and they are in the same position of the matrix. Remember that this is going to one higher order because of the M squared is higher order, right? So that went to leading order. You can also do it to higher order, but then you get other terms. But the point is, we can only compare this MC and MC star. These M squared terms are not going to be contained there because it's leading order. So what happens here is, this is the term that would recover the thing. And you remember that this term here was the quantum state-independent part. And these two terms were the state-dependent part of the quantum one. So if you get rid of these three, this one goes away completely, and this one becomes exactly the classical one. Make sense? If you just replace GF by I delta, these are exactly the same, and they're in the same position on the matrix. And the L terms would just vanish if we got rid of the E and the H. So the thing is, this quantum model is really, it is the quantum version of the classical, and the classical is the classical version of the quantum. In the sense that if you get rid of all of the quantum features of the field, you actually recover the classical model.
What are the conditions to get rid of them? I understand mathematically. Right?
Mm-hmm. Oh yeah, we're going to get there. Yeah, we're going to get there. Cool. Oh yeah, sorry. And then two big differences. Here in the classical case, we had a pure state, right? Because it was two quantum systems with a unitary evolution, just a Hamiltonian. But in the quantum case, we have a mixed state because we also have the quantum field, right? So we have the quantum field, and then we trace out. What's happening here is the two systems are becoming entangled with the quantum field. When you trace out the quantum field, you get a mixed state. And now, well, it's a mixed state, right? And the consequence of the two systems being entangled with the quantum field is essentially why I try to put this picture here. So I'm going to try to explain this picture real quick. So the idea is, picture any quantum information protocol that you want to implement via a quantum field. If your systems now become entangled with the quantum field itself, you're losing part of the information. These are the, okay, you're losing part of the information that is now being in the field. The field itself is going to contain part of this information that Alice is trying to send to Bob. So the intuition essentially is, it's worse to have the quantum features of a field than not to, in order to implement quantum communication protocols. Okay? And we can actually see this explicitly. So consider the setup here where Alice interacts in a region of spacetime here, lambda A. Bob interacts in a region lambda B. And she's going to try to send, to transmit quantum information to Bob. Bob is going to couple right after the light cone and try to read the message that was deposited. Okay? Now, For the analysis that we're going to do, we're just going to assume that these interactions are short, and this is going to be important for the mathematics, but not for the physics. But what matters is that this is the setup, right? Alice interacts here, sends quantum information to Bob, who interacts there. Nice. So in this case, it's possible to compute the channel capacity of the quantum channel established between the two. That's something that was done for the first time by Ericsson and Kensuke. And what happens here is the channel capacity is given by this expression here, where H is just the channel entropy, so the channel entropy function. And this nu B is essentially a term that's associated with the local noise term. So this is the LBB term was the integral of the Whiteman function, essentially, okay, over B only. So nice. So this is the channel capacity for Bob. We don't need to look too much at this expression because what matters is the comparison with the classical case. So the only thing that matters for us is because Alice's interaction happens before Bob's, which is why we need the short interactions, then we can just replace the E by the Green's function, because the advanced one will not matter in this case, because Alice happens before Bob. So this is the final expression. In the classical case, it's simple to get it because essentially you can get it by just simply setting the noise term to 0. So again, you set the part which is intrinsically quantum to 0, and then you get the classical field. What you get is this result here, which is, simpler. But what really matters is that if you compare that expression with this, and use the fact that this, use the properties of this nu, then essentially you can show that the channel capacity, when you use classical fields, in this sense that I'm saying now, is always larger than the capacity when you use quantum fields, right? Yeah.
What is it quantifying?
The channel capacity? The channel capacity of a quantum channel is a way of classifying essentially the amount of reliable quantum information you can send from one to the other. It's like, that's what I can say. I would have to check notes if I want to give you more detail about it. But the channel capacity is a good estimator for how much quantum information you can transmit from Alice to Bob, essentially.
You're trying to transmit classical information or
Quantum.
So quantum information is quantum with a quantum field, or classical information with a classical field?
No. Because you see, what I'm calling the classical field here is the direct interaction between the two quantum systems, right? So you see, if I give you, for instance, two spin-spin coupling, okay? And then I ask you to implement a unitary which is associated with a magnetic field that acts in both or something like this, right? This will act with a unitary there, okay? This unitary will essentially change the state, will change everything about your thing. You can consider that as a quantum channel. There's no quantum field there. You never talked about a quantum field. You never talked about locality, you never talked about anything. You just applied the unitary. You just talked about a field that was shot there and changed the Hamiltonian, right? I'm doing the same thing here, but I'm changing the Hamiltonian according to exactly to what would happen if a classical field sourced by this source did that, affected the other one, take into account relativity by the retarded propagation of the field. So it's like, that's why it's not that weird, because we don't even talk about fields most of the times that we talk about quantum channels. It's rare for us to talk about fields.
Because quantum physics cannot be switched off. We want to impose that we will never in the experiment reach the above the channel capacity, because the quantum is lower than that, and quantum nature is quantum.
Yes, I would like to impose that, sure. For all fields that we're sure that are quantum, yes.
Everything is quantum, huh? That's exactly
I mean,
the point which I want to force you I'm cornering you now because of that.
No, I mean, so I'm going to say that for electromagnetic interactions, for weak interactions, for strong interactions, if you could implement something like this, for sure. For sure that the above is an upper bound, because we know that we can never get rid of the quantum noise, that's impossible. Yes, we know that these fields are fundamentally quantum.
Something in a, for example, B and B, something must be wrong with the definition of classical. Would you agree?
Yes, or you don't have enough resolution to see these new B terms, which are very close to 1. These are the two only possibilities, yes.
If you have a lower resolution, you can transmit more information, you're saying?
No, I'm saying that, how well can you estimate this channel capacity? I think that's the question that has to be asked. If you can really be sure of the channel capacity that you get in the end, and you can really like sense the difference between, because this is e to the minus 2 something small, right? So it's like e to the minus something small is something very close to 1, right? So if you can really sense the difference between the two, you would be able to use it to distinguish. Yes, of course. But that's how it works, right? If you're given 2 models and you have enough resolution to distinguish between the 2, and you make an experiment, well, then you rule out one and you become in favor of the other one, right? Okay. So this quantum-controlled classical field is then always going to be better at implementing quantum communication protocols than a quantum field. I think that's the, yeah.
Could you not implement this kind of with a quantum field such that you don't end up in a new state?
No, I don't think so. I mean, it's a more broad question than just this setup, I guess. And I think that the answer is no. Because the thing is, after you interact with the quantum field, the information that you deposited there is stored in the field. And it propagates.
But I absorb it all at Bob or something, I don't know.
Yeah, but okay, so, but even if you could really create a huge spherical shell that would contain all of the information that Alice had shot, and then interacted there, there would be the vacuum noise at Bob, which is the one that's actually generating this thing, which you can never get rid of. So the answer is no. I mean, I can't see a way of doing this, okay? Maybe there is, but out of my understanding of quantum field theory, no. Yeah.
Second, I don't understand in which sense it is always better. I mean, in the sense which
It's, yeah, it's better because the,
but
yeah.
since I have no intuition about the channel capacity, it's not clear to me. Are you talking about fidelity, about speed of transmission of information?
It's related to fidelity, but not exactly the same. Not exactly the same, but yes.
Compression.
Sorry? Oh, yeah, I forgot to, yeah, sorry about that. Okay, sorry. But yeah. But I think that it's like, again, this is like, I'm not saying that oh, we should just switch off quantumness or anything like this. It's like, what I'm saying is, there are intrinsic properties of quantum fields that make it hard to implement communication protocols there because of its degrees of freedom. It's like, it's this kind of picture, which is like, the quantum field is going to start scrambling that information within itself, whatever you deposit there. And then it's going to be harder to send it because part of it is scrambled in the field and it's everywhere, okay? So I think that's the lesson to be learned. Classical fields wouldn't have this issue. We don't know any fields that are for sure classical or anything like this, so we're probably never going to see this, okay? All right, and the last thing that I want to say very briefly is entangling protocols. And this is less controversial, I think. Okay, so entangling protocols. The idea is it's possible to entangle the 2 systems via the interaction that is mediated by the field, okay? So this interaction can be either via the classical model that I described or via the quantum model that I described. And we're going to consider this setup here, where system A will interact with the field in this region here, spacetime, for this amount of time. This is the size of the system. B will interact for this amount of time. This is the size of the system. And there's this angle theta, which will parameterize where system B is, spacetime related to system A. And so, for instance, if theta is pi over 4, they're really in light contact, right? If theta is 0, then they're completely space-like separated. If theta is pi over 2, then they're completely time-like separated. And L is just the distance between the two. Okay? L is this parameter that's the distance here, and then you just rotate it. Cool. So, and we're also going to consider the case where the interactions are switched in a Gaussian way. And we're also going to consider the detectors to be identical, which means that their energy gap is the same. So in this case, we can actually compute the final entanglement of the system, okay? So in the quantum case, when the detectors are identical, we have this. In the classical case, we have this. And we can use the negativity to estimate the amount of entanglement that the final states have. So in the quantum case, the amount of entanglement is given by this m minus L. So it's the absolute value of this m minus the local noise term, this term that depends on the Whiteman function, the vacuum. And there's that term there. In the classical case, the negativity is given by simply the absolute value of this MC term.
Sorry, on the left
Yeah.
side, this would be entanglement both with the other system and with the field.
No, this is just entanglement between the two. That's actually why we're using the negativity, because if you want to quantify entanglement between the two systems and they're in a mixed state, then negativity is a faithful entanglement quantifier. Yeah? So that's why we're using negativity. But no, this is between the two systems, right? We traced out the field. Also because else we wouldn't be able to compare it with the classical case, right? But I think that the last one here is that the local noise term decreases the amount of entanglement, right? So the noise that happens, this noise associated to the vacuums, it's always going to be there. It's the Whiteman part, the intrinsic quantum part of the field. So yeah, this noise term decreases essentially the entanglement. So let's see what happens when we actually try to plot this. So this is just essentially guessing some parameters. So what happens here if you have, so omega t is t is the time of the interaction. I forgot to mention this, but t is the amount of time that the interaction takes place, more or less, okay? And omega is the gap. So for that value of the gap with respect to the amount of interaction time, we see that the quantum one is the blue one, is always below the classical one. So you could say, well, then the classical is always better at entangling as well. Well, but that's not really true, because what happens is, for this specific values for this small interaction times, essentially, with respect to the omega, we see that there's a big noise in the quantum case. So the negativity should not be that big. Indeed, it's not. It doesn't get even close to the classical one. But now if you start increasing the interaction time, what you start seeing is that, well, now the quantum negativity goes up, right? And what might be surprising if you've never seen this before is that there is even space-like entanglements. For these values of theta, the two are completely space-like separated. Then it might be, how is it possible to entangle things that are space-like separated? Well, what happens that in the end, it's been well known for a while that quantum fields can entangle space-like separated systems. And in this case, what's happening is simply that the two quantum systems are extracting entanglement that was previously present in the quantum field. So the vacuum of a quantum field is an entangled thing itself. And if you couple two systems to this vacuum, it's possible that sometimes you will be able to extract part of this entanglement. So it's like an entanglement swap operation in a way. And this is known as entanglement harvesting. That's the name of the protocol. It's being studied a lot. Particularly nice reference is this last one where they compare the communication and in true harvesting terms, which are the ones that are associated with entanglement previously present in the field, which is kind of related to this. But yeah, point is, okay, if we increase the time, the interaction time, we start seeing the quantum field being better at entangling the probes and getting very close to the classical, up to the point where if the interaction time is very, very large, what happens is that the quantum case pretty much recovers the classical case in this region, and it also is able to give entanglement in the space-like separated regions. So essentially, the two conditions so that the quantum and the classical case can behave similarly for these protocols is that, one, the interaction times are very large compared to the natural frequency of the quantum systems. And two, the systems must be in causal contact. They must be in causal contact because otherwise the quantum field is going to start getting the entanglement that is, well, the detectors will start getting the entanglement that was already there in the quantum field. Nice. So, yeah.
Can you explain why them touching has something to do with, like, what they're not touching there? Why is there not?
Yeah, sure. So if you come back to the expression for the negativity itself, so remember that this m, it's the integral of the Feynman propagator, which is essentially the imaginary part of the propagator is exactly that, and there's the real part of the propagator on top of it. Okay, so this is essentially the m is mc plus another term inside this absolute value, and this local noise term is the vacuum noise term, right? It's the noise that is seen by the detectors. So what's happening is the mc is here, but then there is another term here which is fighting this L, and they're competing. So if L is too large, L is going to be large enough to even overcome the MC. to even overcome that term, and then you're not going to see, you're going to see the quantum case losing for the classical one, which is what's happening here, okay? And this local noise term, it essentially decreases very fast with the interaction time. So that's why we're seeing this behavior. And you can show that the maximum that you can achieve in the quantum case is always going to be the maximum that you can achieve in the classical case because of a comparison, not always, but in the limit, because of a comparison of the extra term that you get in the quantum case and the local noise term. You can compare the two, and then you get you get this. Okay, cool. But yeah, so essentially these are the two conditions. Overall, these examples allow us to formulate conditions so that a quantum field can be well approximated by a classical field. And these three conditions are, well, one, they have to be causally connected, because only quantum fields can entangle spatially separated things. Two, long interaction times, so it's this condition here, t much larger than the characteristic time of the quantum system. And the quantum systems must be weakly interacting with the quantum field. So this assumption is kind of key for everything that we've done so far. We've been using perturbation theory, but also like if you start having very strong interactions with a quantum field, then you might expect the quantum field to really behave differently from a classical field, particle creation, and whatnot. So you need weakly interacting systems.
So, sorry, for the first point,
yeah.
they will have a contribution also from the vacuum entanglement, even if they are causally connected. Am I right?
Yes, but when they are like really in light contact, then what happens that this contribution is small, very negligible in the limit of long times. Yes. So it's yeah. So under these three conditions, then a quantum field can be well approximated by a quantum-controlled classical field. Okay, nice. So summary. Okay, regarding relativistic quantum information protocols, classical fields perform better at these protocols if the systems are causally connected. That's given. The quantum degrees of freedom of a quantum field, the issue, right, is that the quantum degrees of freedom of the field produce this noise, which is detrimental for the protocols. Okay. Also, only quantum fields can entangle spatially separated systems, and this is something important. There are specific conditions to when a quantum field can be approximated by a classical field, which are the three we just discussed: causally connected, long interactions, and weak interactions. So long and weak in intensity. Nice. So these are the three conditions, right? Okay. Well, it's been an hour. I have the BMV part that's very short, but I think it's the. Okay, I apologize for not rehearsing this. Okay, cool. So applications to quantum gravity. So okay, now that we know the main differences between the quantum and the classical things, we can really apply these things to the BMV experiment. I'm guessing that most of you have already seen the BMV, but if you haven't, I'm just going to very briefly describe it. The idea is that you have two masses, M1 and M2. They undergo a superposition of two trajectories each, Z1, well, left and right for each. And then, if the particles interact only gravitationally, they might become entangled. And the question is, if we're able to see this in a lab, what does it mean about the gravitational field? Does it mean that we've witnessed quantum gravity? And okay. So now that we have the two formulas, the classical and the quantum one, we can just apply them to this case. Okay. So using the relativistic classical field interaction discussed before, we can actually adapt it to the gravitational field. We use linearized gravity, and then essentially the interaction is going to be a sum over paths, projectors over the different combinations of paths, and this phi, which is simply the gravitational interaction between the masses. And if you do it relativistically, what happens here is that the gravitational potential, the effective gravitational potential, ends up becoming a contraction of the T mu nu of the masses, the stress energy tensor of the masses in each path, with the field sourced by each mass in each path. So each possible path sources a gravitational field. Then they couple to the corresponding stress energy tensor, and you sum over all combinations and projectors over each one of these. So it's pretty much in the same spirit of the things that we had before. It's essentially use the classical propagator, right? Because then you just replace these by the propagator. Okay. Now, if you want to describe the BMV, usually in the original formulation, people use this maximally superposed state. So it's essentially maximally superposed in both paths. And then after the interaction with gravity, you can actually show that I'm using the negativity again to quantify the entanglement. I mean, in this case, you could use others because it's a classical field, it's just 2, but okay. Now, you use negativity, and you find that this is the final result. This is the first order expansion. And what really matters here is that this delta is now the contraction of the, so it's got 4 indices, but it's still the GRGA. But we need 4 indices because we're handling spin 2 fields. And it's contracted with the stress energy momentum tensor of each path. So delta L1, L2 is this contraction here, but now using path left 1, path left 2, and same combination for each one of these. Okay. Okay, so this is the result for the expected entanglement using this protocol. Now, we can also do the same thing using linearized gravity, linearized quantum gravity, sorry. So essentially what you do is that linearized quantum gravity is this weak field limit is expected to be the weak field limit of any theory of quantum gravity. And you treat the gravitational field as a spin 2 free field, and then you obtain the quantum field theory for that. If you apply this formalism, now the same difference that we saw before, that we had instead of lambda squared, we have lambda. So the lambda here is square root of g, essentially. That's what happens. And the masses will be coupled to the linearly quantized gravitational perturbations via their stress energy tensors. So now there's no propagation of the field, that's just the coupling. And again, this is stress energy tensor, and this is the linearized quantum gravitational field. And this is the model. We can just literally start with the same states and compute what would be the final state of the masses. I'm not going to write the final state because it's kind of big, but the negativity reads this. Okay, the negativity of the state reads this quantity here. So now we have the g instead of the delta. Remember that the delta was the contraction with using the delta and the t's. Here we have the g. G is just the final propagator. It still obeys the same thing that it did before. So its imaginary part is still 1/2 times the delta. And so essentially, this is the result for the quantum field. And we again see these local terms decreasing the amount of entanglement, right? So essentially subtracting from the negativity. It's as if these g's were like the m terms, and this l was the local noise term subtracting from that. But the point is, if we compare the quantum and the classical case, we see that they're very similar, except for a factor of 2, the local noise terms, and the g and the delta. Well, it's a good thing that the g is I/2 the delta, and everyone's inside an absolute value sign. So you can see that if the local noise is 0, and we neglect the state-dependent part, they are actually going to be the same amount of entanglement, right? The classical and the quantum case. But what really matters here is that the two are different. The two results are different. So in principle, someone could experimentally decide whether one or the other is describing this more properly, right? The experiment better. So the question is whether it's possible to notice these in the original experimental proposal, right? So if you use the setup that is being considered in the original papers that promoted the BMV, would it be possible to distinguish between these two cases? Well, what happens is the original formulations of the BMV use long times. They do this in order to maximize the entanglement acquired. Because remember that the negativity was a sign in the classical case. So if you let everything interact for a long time, the sign starts building up, and if you stop this at the right time, then you can actually get a maximally entangled state almost, depending on the setup. And this is a key ingredient also so that the phenomena can be observed in the laboratory with current technology, because you need a lot of entanglement in order to be able to witness it. A consequence of these long times and the short distances that are used there is that the systems are always causally connected throughout their interaction. Okay? They're very slow systems that they really, and then they come back. I mean, it's much longer than this, but whatever. Speed of light is large. And finally, the gravitation interaction is very weak for the systems that are proposed in the implementations. Of course, the tabletop experiment, right? The thing is, these are exactly the 3 conditions that we saw, which ensure us that classical and quantum fields will behave very similarly, and it will be nearly impossible to distinguish what one or the other, because exactly of the the similarities between them, and if these 3 conditions are satisfied. If one of them is violated, we can distinguish them, but if the 3 of them is if the three of them are satisfied, then they will behave very, very similarly. So that's why Eduardo and we came up with this idea. It's very simple to state, but it's very hard to implement in the lab. So, well, given that only quantum systems can entangle things that are causally disconnected, and classical fields cannot entangle things that are causally disconnected, then we can just adapt this so that now the trajectories are space-like separated throughout the interaction. And now if we see entanglement, we can make sure that we witnessed entanglement that was previously present in the gravitational field. Now, shielding this and implementing this will definitely be hard, but this would be a definite proof of quantum gravity. Okay, and that's it. The conclusions of the talk, and then now we can really discuss about the BMV experiment as much as we want. Okay, so I think that these are essentially the conclusions that I can take from this whole discussion about the BMV experiment. It can determine whether gravity can entangle quantum systems, that's for sure. If you get two systems that are interacting via gravity and they end up entangled, gravity entangled them. So same thing, establishing a quantum channel, of course. It tells us, in a way, how gravity couples to quantum systems, right? This would rule out many theories of classical gravity, such as semi-classical gravity, and some theories of stochastical gravity, which is great. It's good to rule out some theories. It is completely agnostic to quantum degrees of freedom of the gravitational field. There's absolutely nothing in that experiment that I need to use the quantum degrees of freedom of gravity in order to describe. That's why this classical model works. And the experiment might say something about superposition of gravitational fields, depending on your definitions of superposition.
Can you explain what is semi-classical gravity and stochastic gravity in your terms? Because I'm not sure any.
I'm going to send you to Edu for the stochastic gravity. Semi-classical gravity, sure. You're going to source gravity by using the expected value of T mu. Okay. That's what I call semi-classical gravity. Okay. Yeah. For stochastic gravity, there are many theories. I don't know enough about any of them. Eduardo does, so I'm going to point you to him. Cool. So that's it. Thank you so much. Really appreciate the, yeah.
But your conclusions in the end, you're talking about the BMV experiment or your modified one?
I'm talking about the original one. The modified one could just see entanglement in the gravity. Yes. Thanks for the question. Oh, right. Yeah, I'll repeat every question that's asked. So, yeah.
So there was the regime where the classical negativity due to the classical field, due to the quantum field were different, and this had to do with the time. So,
yeah.
So for longer times, you had they were closer.
Mm-hmm.
So one way to understand it is that the noise, you overcome the noise because you have more integration time, right?
Mm-hmm.
But could you also understand it as you don't emit gravitational radiation because the experiment, because the period of the field is longer than the time of the experiment? No.
Yeah, they're both ways of understanding this. This vacuum noise, it can be associated to many things. So, for instance, we have the switching function in front of the Hamiltonian, right? This is a Gaussian switching function. So what happens there is that if this t is very long, then it's an adiabatic switching, right? And the thing is, if t is short, if there are changes in chi of t, then your interaction Hamiltonian explicitly depends on time, right? Like, it depends on time. So this means that it violates energy condition in a way, right? And it's not that it violates energy condition, it's that you have to input energy into your system to switch the interaction on and to switch the interaction off. And this can be seen as one of the causes of the local noise terms, right? But at the same time, if you do it, you can think in terms of the gap of the detector being large enough in order to sense the effects of the field and whether these will be washed out or not. Yes, the emitting, yeah, the emission of radiation is not not radiation, right? But it's because again, the emission happens because of the switching. That's something that has to be kept in mind, right? It's like when you switch it on, switch it off, that's when this emission happens because you're effectively messing up with the system, right? So, but I think that the best way of understanding this in terms of the just adiabatic switching, like you see nothing in the vacuum if you're interacting with the vacuum for a very long time. But if you're interacting with the vacuum for a short time, then you're going to see a bunch of noise, which is where this is coming from, essentially.
You have some Gaussian switching, like it's infinitely long, but you still have some Gaussian switching from within. Yeah, many switches.
Well, if it's infinitely long, it's not a Gaussian switching, right? But I mean,
No, but I mean, the standard deviation is still short enough. Like, is this because you have an abrupt switching? You should have the same effects and still what you call quantum gravity, even if you have.
so I'm not talking about gravity here. I don't think that it's like, yeah, yeah. That's the important thing. Yeah, yeah.
There are two parameters that you can separate. Here they are both described by this capital T, but you could also say that your switching is very fast, so you can emit radiation, or you switch it very slowly, so you don't emit radiation, and then you're flat for a long time, so you overcome the noise, or for a short time, so you don't overcome the noise.
Yeah, I think that this
And
is,
then you
yeah.
don't really see which one of the terms, so emitting graviton or the local noise.
I see.
Which one really
I think that,
messes up the entanglement.
But I think you have an effect without radiation. You want to say that?
yes. There are two effects, that's for sure. But yeah, no, that's a good point.
There's background noise and then there is emission. That's the point.
I'm sorry?
The two effects. There's emission and background noise for the detector.
Yeah, so in this case, I wouldn't say emission. Like in this case, it's the opposite, like absorption, because you start with them in the ground state, right? And it's like you're not gonna emit something if you're already in the ground state. But it's like if you interact with the vacuum has like it has excitations due to quantum uncertainty, quotation marks on everything I say. But it's like the thing is, if you interact with it, you might be, if you interacted with it for times that are too short, you're gonna see very small wavelengths with big oscillations, and then you're going to get a noise out of this. This is a way of thinking about this. But yeah.
Very different question, maybe a little bit weird for you. So negativity is bounded by one. Log D in this case.
It depends. It depends.
If you have two-dimensional system, it's log D.
Yeah.
It's actually asking about this graph that you showed because
No, it doesn't matter. it's going to be, so the convention that I'm using here is going to be bound by 2. It's going to be bound by 2. I think so. No, I might be wrong. I'm not sure. So what is the, no, it's, is it going to be bound by 2? No, never mind.
what is log D? So if these
But the thing is, it doesn't matter whether you multiply your negativity by any positive number, or whether you take the exponential or the log or anything like this, right? So that's what I'm saying. The negativity that I'm using here, it's not going to be bound. It's simply the sum of the negative eigenvalues of the partial transpose of the matrix. It's just that. So I'm not taking any log, right? So that's why I'm saying that because that's the thing. It doesn't depend whether you exponentiate or.
But so in your graphs, like all these numbers you give, like all the graphs, they look the same, but then the left, like
Yeah.
the y-axis actually scales vastly different. There's like 10
Yeah.
to the minus 200,
Mm-hmm.
10 to the minus 7. There's like,
Yeah.
does this mean you have a negativity of 10 to the minus 200? It's like how will you ever be able to tell it? It's like even a negativity of 10 to the minus 7, I guess, in this context is like vanishing this small that every
So.
error bar would just
Yeah, the answer is so. Okay, so these are bad choices that I've made for displaying the numbers. Okay, and the reason for this is because in these examples that I did, what I was trying to actually aim for is values of the L and because the thing that really matters is the distance between the two, right? So the thing is, I wanted this L to be such that, L relative to T, to be such that I would be able to get space-like entanglement, and I would be able to make sure that the detectors were still space-like separated in this case. Because you see, I'm saying that they're space-like separated, but if the detector interacts for this time, then theta is 0, and L is this, they're not space-like separated, right? I mean, super causal contact, right? So this is the interaction time of the detector, right? This is the T. This is the region where they interact. Let me go back to the picture there. It depends on what you want, and it depends on many things. It depends on many things. So what I'm going to say is, you see, if I use a small value of L, they're going to be in causal contact, no matter the theta, right? So what I did in that case, because we have a Gaussian switching, right? The standard deviation is 7. It's T, sorry. So for these plots, what I did was I considered that the actual support of the Gaussian was 70, so I pretended that it had a support of 70, which contains like 99.9999% of its area. Okay, so I said, okay, so this is where the detector is. This is what I call T, contains 99.9% of the area of the Gaussian. So this is 70. Then I consider a distance of 17T between the two. Okay, so I don't know, up to scale it would be something like this, I guess, more or less. So that's why I go with very, very small numbers, because I was very conservative about whether they are space-like separated or not, and things like this. I could have just used a switching that was 0, then became 1, then became 0. This could have helped, this could not have. I actually have some cases with switchings that are kind of like this, but using a cosine profile that is 0, then cosine and things. And the values are better. They're not amazing, but they're better, right? No, 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 no. No, so entanglement harvesting has never been seen in a laboratory. There are future experimental proposals that want to implement this, but they're very smart there, because actually they're not just doing this, I don't know, in a standard vacuum. They have like the idea is to have a huge cable that will be like a cavity for the field. Then you can make that thing be massive, like in size, and then you can effectively spatially separate the system, right? So, but yeah, the answer is like it's hard. No, it's hard, because the issue is like how to control these things, and yeah, sorry.
So I have a question concerning classical field. I mean, what it seems to me like is that your classical field is just basically the DC value of the full field, kind of, so like the longitudinal component or something in QED, right? I mean, so for low switching speeds or something, the classical field and the quantum fields are the same, right?
Yes, I guess. Yes,
yeah, so
they're more. Yeah.
Yeah. So I mean, I fully agree with your statements that the DC field or whatever, Coulomb field or whatever, there's no degrees of freedom. It doesn't need its own Hilbert space and all these things that you said. That you would say, oh, this is a classical field, right?
Mm-hmm.
Okay. So I agree with that, right? So and then when you do this entanglement, right, you basically do it a little faster, right? So you do try to send information, and so in one case you have this full quantum field where you cannot excite infinitely fast without exciting higher modes and kind of losing the information, right? And on the other hand, you have a classical field where you cannot excite at all, right? Because it cannot carry energy. So you basically have a super field, basically. It's a field that can do more than the other ones, right?
I mean, it can do more of some things, right? For instance, it can't entangle space-like separated.
You can turn it on and off, right, without ever putting any energy into the field. So your classical field never carries energy.
I don't know if that's not true. That's not. I mean, the issue is how do you even go about talking about the energy in the field, right? Because
For me, what is the best kind of picture in my head about the dynamic degrees of freedom and the DC values, like Coulomb field and radiated modes. So the radiated modes obviously carry energy, and the do behave.
It's not even in a quantum case. I mean,
no, but I mean, but you see.
But it's own Hilbert space
No, but you see, if I give you a charge, right, and I twist it and I rotate the charge a little bit, okay, and you use the retarded propagation, you're gonna see you're gonna get your field. You're gonna get your field, right?
That's a photon. It is radiating.
Yeah.
No, but if it's strong enough, it's not, right?
Yes.
Yeah.
If you see fluctuation of the electric field at a classical level, there is the
Yeah.
emission of a photon. There's radiating energy.
No, I mean to see if you move the field, you will see the change somewhere else without having to radiate.
That's
No, I think this is what the super field does, right? You change the field, but you never radiate. Well, anyways, this is just how I would see this. So I mean, basically what I want to say is the classical field you described to me is like the Coulomb field of the full thing.
The Coulomb field of the full thing?
No, I mean, so you have the electromagnetic fields, right? And the Coulomb field is basically the slow field, right? So if you move stuff slowly, you only have the Coulomb field. So just from a classification point of view, it seems like
No. This field takes into account retarded propagation, like literally. If you, yeah.
It's okay, in that sense it's better than the Coulomb field. If the Coulomb field doesn't have any radiation, I understand. But I mean, to me it seems like from a classification, it's just so for lower speeds it's the same as the quantum field.
May I interfere? Maybe I will.
Sure.
I can help. As far as I understand, the one is Coulomb with retardation. That is what is called classical. The other is Coulomb with retardation, but such that the components of the field that corresponds to electrical magnetic components, because it's not just a Coulomb field they move, do not commute with each other. So there are some components of the field that do not commute with each other. There is no radiation. I mean, there is radiation if you make it up or change, but apart from this, this is not the effect you want to describe, I guess, not radiation. So even if the radiation is suppressed, there is difference between the two, because in one case, classical, it's just slave of the matter with no inherent degrees of freedom that are not commuting with each other, whereas in the second one, they are.
What is the second one?
The second is the quantum.
So you mean the quantum one, there are more degrees of freedom even if it's slow, basically.
Even if it's not.
Oh yeah, I mean, there's nothing intrinsically fast about the things that I discussed here. You're coupling to the field, but yeah, I mean, you could argue that if t is large compared to omega, maybe, I don't know. But
have like now a little bit, I mean, of criticism of the denominator. I think you have a nice result. So I don't understand why you want to use the words that community does not, for good reasons, does not use. Because I mean, your title was, I don't know, classical fields entangled.
Can a classical gravitational field entangle?
Theorem, quantum information that tells you you can't do it with the classical system. So if you have a theorem, why should you use these words? Secondly, I mean, after all, really in BMB, even in the classical regime, you can violate Pellet's inequalities. There is no more stronger evidence that it's not classical.
No, but Bell's inequalities for what?
Sorry?
Bell's inequalities for what? Sorry.
For two masses.
Oh yes, of course you can, but that's not enough. Because again, being able to entangle systems, it's like.
No, don't tell me so now, and don't use quantum words. I'm talking about the effect that has nothing to do with the quantum theory that proves you something is not classical. That's violation of Bell inequalities.
Yeah, but this violates the masses, like, you're not violating in the field.
Okay, that's another thing, which is what I don't fully understand. You said I agree with this. Is either there are degrees of freedom of the field, or they are not. If they are not classical. Not only that they are not quantum, they are not no degrees of freedom. That's one part to follow, and then you say there is no field involved. Two masses violate Bell inequalities, but I don't care. They interacted directly. Or you do talk about degrees of freedom, even if they are slaved by the matter. But then it's just doesn't make sense to say, oh, I have a field that slaves the matter. Matter is in quantum state. Then you follow the logic. The state slaves the matter, but suddenly the states of the slaves are matter, but fields are classical. And it doesn't make sense. If they are slave to matter, which is quantum, they must be together in matter quantum. Let's say semi-classical, maybe quantum control of classical is also nice. I think this is a good wording. Just to make a distinction.
No, I agree that quantum controlled classical is the right one, but it's just, okay, maybe QCC, right, for quantum controlled classical, because it's hard to say it. That's why I wasn't using quantum controlled classical always, but I think that that's the, I agree with you that that's a better name. I'm not going to say that it's not, because.
And now what I like about this is that this LCC theorem was with the idea that you have system A and C, and then there is a system B that interacts with A, or system B interacts with C, but A and C never directly. And then you prove that if A and C get entangled, B must be in some non-classical.
Yep.
That was the theory. And that was the idea of the whole. But now what you said, sorry, this is not the situation in reality, because the B is from very beginning, non-locally, so to say, entangled, vacuum state of the field is entangled. So what you prove is not that there is interaction between A and B and C. There is just kind of an entanglement swapping by a local interaction. Because if you have a B that is spread over A and C, and B is entangled on both sides where A and C are, then only by local interaction you can swap already existing entanglement in B into A and C. So that's the argument, what I want to say. The original argument didn't take this into account. And I think this is something very conceptually what you can say. Sorry, but the nature situation is not like what you think, because there is always vacuum. And vacuum is always entangled, so most maybe what you do is entanglement harness could be. Now, of course, the answer to that is, okay, let's calculate in advance how much is this. But it's already a little bit pulling back the argument, saying, okay, so the only way to say this is to say that if this effect is very small, and the most of the effect is due to really original argument. But I feel that this is something what you should put more
emphasis in. Yeah, I mean, I should have discussed the whole locality argument about the conclusions of the BMV. It wasn't really the focus of the talk. But I think that that's something that could kind of be used to address this. Because I think that this whole idea of, like, sure, you have systems A, B, and C, and then A becomes entangled with C, V an interaction that goes through B, right? The thing is, what if there's no B? And that's essentially what's happening here. There's no B, right? And then there's no theorem that you can come up with that is going to be applied to this, because then you just have an interaction between systems A and C. And this interaction entangles them. And
I think that one can maybe formulate that B is a system, but not in the original paper. This is not the case. But we can discuss it.
Yeah.
You want?
Yeah, I just had a small comment that like the definition of a classical field that we usually use is a field that is invariant under the coherence. And is it yours invariant under the coherence?
Yeah. I wouldn't even be able to tell you what is the classical field in that case. I would say that the classical field is this retarded propagation interaction, right? It's like, it doesn't exist as an entity if you're not interacting with it. It only exists if you're interacting with it, and then if you are interacting with it, what you're going to see will be, your local Hamiltonian will have a term there that will say, there is retarded propagation that came from that point, and you're now becoming entangled with that, right? So it's definitely something that is not a standard classical field. It's definitely not like yeah. I would say that, yes, it's invariant under, there is no decoherence in this field because there's no Hilbert space for this field. So it's very easy to say that there's no decoherence. No, I'm kidding, but it's like,
The word is quantum. All systems are quantum. There are some which we can treat classically, and those that are invariant under the coherence.
oh, right. So in that sense, well, yes, because you saw, we got a pure state in the end after they interacted via the field. Is that because, I mean, one of the main differences between the quantum field case and the classical field case is that in the quantum field case, you had the two systems, and they became entangled with the field itself. That's why we got a mixed state. But when these two systems interacted via classical field, they still ended up in a pure state. Entangled between the two, for sure, but they were still a pure state. So yes, in this sense, it is a classical field.
I don't think it is.
Hmm?
At least if you go to the quantum information formulation of it, it's clear that this cannot be.
No, but well, two systems that interact via it, via this field, will not experience the coherence with the field itself. That you can say. That is true simply because they will always be in a pure state.
But that's not the point. I mean, the question is the field itself. If the state of the field itself is going to be invariant under the coherence. But yeah, but you cannot.
There's no state of the field. Yeah. Yeah.
You cannot ask the question.
Well, it's a vacuity answer. Yes, it is invariant. No, I'm kidding. But yeah.
So maybe we should stop at this moment.
Right. Thank you for the invite. This is nice. But I think that the main purpose of this is it's way easier to do calculations with the classical case, and it is a good approximation for the quantum field in some regimes. So I think that that's something that is like, I'm not advocating that this is the most fundamental description of anything, but I'm just advocating that it is the classical version of the interaction with a quantum field. It's what you get when you strip the quantum field of all of its quantum features, right? But of course I don't believe that this is what should describe gravity, no. But I also don't believe that, given that this exists, gravity, given that there are other possible descriptions for the experiment that are just like literally the classical version of the quantum field case, are you going to say that that proves that gravity is a quantum field? I don't know. That's my issue. Yeah.
The argument is quite clear that you say you strip it of these properties, right?
Mm-hmm.
But why is it a classical field because you strip it of these properties?
What do you mean? Well, no, but these are exactly the quantum features of the field, right?
The terminology to call it a classical field is weird, to me at least.
I mean, I give you a quantum field. I point exactly what are the things that are quantum about that field. The state dependence, the non-commutativity, all of this, okay? Now I go to you and I give you the same field, but I take these away. I set all of these to 0. What would you call that? Because I will call that a classical field.
Not a dynamical field. So to me it sounds like the dynamical aspect. So for me it's just an analogy to QED, right? Where you have these fields that so basically where you have the DC fields, the Coulomb fields, whatever, and then you have the radiating stuff and the other components. So to me I would call it just a non-dynamical field or something that doesn't have energy or something.
To me, if I give you a quantum field, yeah, okay. I mean, but again, that model is a toy model, but I think that what is really the key thing is, you see, what is necessary for the BMV experiment is exactly the part that doesn't depend on the quantum aspects of a quantum field. It just depends on that one part, which is the same thing that you get in the classical field.
I would fully agree that it doesn't depend on these properties,
But these are the very properties that define a quantum field. These are the very like the commutation relations of the field, right? The dependence of the states of the quantum field. These are the things that make that a quantum field instead of something else. So like whatever the BMV proves, it doesn't prove that. It doesn't prove.
I mean, what for me would be a classical field is something like semi-classical fields, right? I mean, your field doesn't sound like that at all.
No, it's not. It's definitely not. No, it's not. But the thing is, in this case, we don't need any experiment in the sense that